So you have a little while to finish the chapter 23 quiz on Blackboard. It's due on the 9th. So that's tomorrow. It's 40 minutes. You need to do it in one setting. You get one attempt. You have 25 questions, and the short answer questions will be graded manually. Most of you have done it, so I'll be grading those after the due date. I'm still working on grading the tests because things take time. Chapter 23 homework is due on the 10th. Chapter 15 homework is due on the 17th. So we're starting chapter 15 on place and time. So we'll talk about what a Cartesian coordinate system is and explain what the numbers on the X and Y axes indicate in a rectangular or Cartesian coordinate system. We'll differentiate between lines of latitude and longitude. We use latitude and longitude to find the location of specific places on the Earth. We'll differentiate between a solar day and a sidereal day. We will talk about the organization of time zones across the world. We'll look at the differences between the Mercator projection, the Peters projection, topographic, geologic, and bathymetric maps. And this is about maps, how to read them, how they work. We'll talk about how to analyze differences in elevation and interpret common informational symbols on topographic maps, in addition to determine changes in distance, elevation, and gradient on topographic maps. We'll talk about how you determine an observer's latitude and longitude from the altitude of the sun, from the position of the sun. We'll explain what gives rise to Earth's seasons. We'll describe the position of the Earth in its orbit around the sun during the seasons. We'll describe the overhead positions of the sun during the solstices and the equinoxes. And we'll describe the length and effect of Earth's precessional period. So, if you want to talk about where something is located, you need a reference system with one or more dimensions. Dimensions are basically just directions or, directions that you can measure at some level. So here, a one-dimensional system is shown below. It's just a straight line. You could have positive values or negative values. It goes from positive infinity to negative infinity. You have to indicate an origin, a starting point, and units. So how far you are from some other position. So examples of one-dimensional scales are things like temperature scales, left and right, above sea level, below sea level, profit and loss. They're described with one number at some basic level. So they're one-dimensional. Now, Cartesian coordinates is a two-dimensional system in which two lines are drawn at right angles to each other, perpendicular to each other, with an origin assigned at the point of intersection. This lets you measure things, up and down and left and right, or just in two directions. So in general, the horizontal line we call the x-axis, the vertical line we call the y-axis. Up and down is y, right and left is x. So the system we commonly use is called the Cartesian coordinate system. This is because it was created by the French philosopher and mathematician René Descartes. So Cartesian, carte from Descartes. You'll find a bunch of, if you take other classes like philosophy and things, you'll find other things that are called Cartesian. That's because they were created by René Descartes. So all Cartesian things can be traced back to Descartes. And Descartes was one of the earlier people working on what's called algebraic geometry, algebraic geometry, where he was actually trying to apply numbers to geometrical figures. And so he built the Cartesian coordinate system to be able to talk about where points and lines and such were located. And this is used in pretty much all flat two-dimensional surfaces. So Cartesian coordinates are two-dimensional. The x number gives you your left and right position, your distance from the y-axis. The y number gives you the distance from the x-axis, up and down. So many cities like Chicago are laid out in a nice Cartesian coordinate system. Chicago addresses are on a Cartesian system. So streets are running north, south, and east, west. And every 100 is an eighth of a mile, if I remember correctly. Yeah. 100 in addresses is an eighth of a mile. There are 8 blocks to a mile. So if you want to determine where a point is, X and Y will locate a point. And because we want to talk about where positions are in Earth and in space, we need a system like this. So if I wanted to talk about this point here, that would be 2, 3. 2 in the X, 3 in the Y. And that would be this point here. If I was at 3, 2, I would go 3 in the X and 2 in the Y. And if I was at like -2, -2, you're -2 in the X and -2 in the Y. That'd be about here. So location on Earth will be determined by means of a coordinate system. On Earth, we have a coordinate system called latitude and longitude. It's two-dimensional. There's a north-south and an east-west. And since the Earth turns on its axis, we can use the poles as reference points. So yeah, this is a globe. It's a model of the Earth. The poles make natural reference points that we can draw lines from. But this isn't exactly the same as a Cartesian coordinate system because this is a sphere. It's not a flat surface. So the geographic poles are the imaginary points on the surface of the Earth where the Earth's axis projects from the sphere, where the axis of that globe goes. And then the equator on a globe is this line in the middle. Is the imaginary line circling the Earth's surface halfway between the north and south poles. The equator is what's called a great circle, a circle on the surface of the Earth in a plane that passes through the center of the Earth. So if you draw a circle on the Earth, that's made by cutting a slice through the center of the Earth, that's a great circle. The equator is one of those. So here is a short video clip about latitude and longitude. I thought apparently I misclicked. Okay. Oh.
Earth, our home in the vast universe. The Earth's circumference is nearly 25,000 miles from start to finish. There are so many places on the Earth. How is it possible to precisely locate just one of them? For instance, what if I wanted to tell a friend the exact location of the Coronado Bridge in San Diego? It would be hard to describe, but give him the coordinates of the bridge and he should be able to find it quite easily. To find precise locations, parallels of latitude and meridians of longitude form an invisible grid over the Earth. Latitude. Lines of latitude, also known as parallels, circle the globe from east to west. These lines are all the same distance apart, about 69 miles. Each degree of latitude is separated into smaller pieces called minutes. There are 60 minutes in 1 degree. Similarly, each minute is divided into 60 seconds. The equator lies at 0 degrees, halfway in between the North and South poles. There are several other unique lines of latitude. The Tropic of Cancer lies at 23.5 degrees north, and the Tropic of Capricorn lies at 23.5 degrees south. The part of the Earth that lies between these lines is called the tropics. It's known for its hot temperatures, heavy rainfall, and dense jungle. The Arctic Circle lies at 66.5 degrees north, and the Antarctic Circle lies at 66.5 degrees south. The area of the Earth between these parallels and the tropics is characterized by 4 distinct seasons. Longitude. The lines that run north and south are called meridians of longitude. These lines are measured the same way as parallels of latitude using degrees, minutes, and seconds. However, unlike latitude, lines of longitude are not equidistant from each other. Meridians intersect at the north and south pole. 0 degrees longitude is called the prime meridian. It passes through the Royal Greenwich Observatory in Greenwich, England. Using latitude and longitude, the precise location of San Diego can be written as 32 degrees, 42 minutes, 54 seconds north latitude, 117 degrees, 9 minutes, 25 seconds west longitude. Parallels of latitude and meridians of longitude form an invisible grid over the Earth. This grid is measured in degrees, minutes, and seconds, and it allows us to pinpoint exact locations anywhere on the face of the Earth.
So, meridians are lines from pole to pole that separate the Earth into, we use them to measure east and west. Parallels are horizontal slices through the Earth. Meridians are all half of a great circle. The parallels vary, but the equator is a great circle. All the other ones are not. They are all circles that are used to measure north and south. They measure between the North Pole and the South Pole. So latitude. So both of these are measuring angle. And so there's 306. Well, latitude measures the angle north and south. So if you draw a line from the Earth's center and then a line out to the equator and a line from the Earth's center to the place you're looking, you get an angle. That angle is the angle of latitude. The latitude is the angular measurement in degrees north or south of the equator. And that is measured from the center of the Earth relative to the equator. And so lines with equal latitude are circles drawn on the surface parallel to the equator. So their slice is parallel to the equator. As you can see here, these are lines of equal latitude. They're slices through the Earth parallel to the equator. And they go from 90 degrees south to 90 degrees north. And you can have subdivisions within them of each degree has 60 minutes. Each minute has 60 seconds. Exactly like it is with time, except in fact, those divisions existed in angles before they existed in time. They were picked up from angles for time. But the minute comes from the Latin for like division, minuta. And second comes from minuta secundus, or second division. So second actually comes from second, like the second option. Latitude is also called parallels because they're all parallel to each other. They're evenly spaced. They're an infinite number from 0 to 90 degrees north or south. And going from the equator to the poles, these represent a series of complete circles where the equator is the largest, and then you get smaller and smaller going north and south until they hit the poles, where they become infinitesimal. At the pole, at 90 degrees north, it's just a point. And the point on the opposite side of the Earth will have the same value. So 40 degrees north is opposite 40 degrees south. So, I don't know, what is the latitude here? So now we're at 41.7 degrees north. Does it have it in minutes and seconds? Oh, yeah. So 41 degrees north, 40 seconds and 40 minutes and 16 seconds. At least according to my GPS. So latitude is also called parallels. Longitude is the measurement east and west. Latitude has natural reference points, the equator and the poles. Longitude, well, we're in a ball. You can start anywhere for 0. So in fact, for a while, there were multiple different systems of longitude with different zeros. And then there was a big meeting, everybody got together, and the Greenwich 01, because at that time, Britain and the US were up and France was down sociopolitically. The biggest competitor was Paris. So longitude is an imaginary line drawn on the surface running from the north to south pole, like this, and they're perpendicular to the equator. Lines of longitude are also called meridians. Each line of longitude is half of a great circle. And there are, of course, an infinite number of lines that can be drawn as meridians because you can choose any angle you want. So if we're talking about where we are, I will write it out in, we are at 41 degrees, 40 minutes, 16 seconds north, and 87 degrees, 29 minutes and 39 seconds south, and not south, west. Or as it's more commonly written these days, you can write it as 41 point, what is it, 6711 north, and 87.49 4, 4942 west. I don't know if that's the right number of decimal places, but that's sort of a rough thing. I actually probably should have some more decimal places, but no worries. So you can express it in minutes and seconds, or you can express it with a decimal. And there are an infinite number of lines that can be drawn as meridians. So longitude is the angular momentum measurement east or west of the reference meridian, the prime meridian, which is 0 degrees. It's at Greenwich, England, the Greenwich Observatory. There was a large telescope there that was used to define the reference for the system. That reference actually moved a little over time, and has in fact moved a bit since then. But there is, if you go in the building of the Greenwich Observatory, you can see how it moved, because there was, first they used that telescope, then down the hall, there's another telescope that was better. So they used that instead. And now the modern one is actually like 100 meters or so outside the building in a park, because it's defined by satellite things and it's moved a little off. So the maximum value for longitude is 180 degrees east or west. So if you're at a spot on the Earth where the longitude is 80 degrees west, the opposite side of the Earth, you'd be at 100 degrees east. So to get the opposite side of the Earth will be, for latitude, you just switch from north to south, or vice versa. For longitude, you switch east and west, and then you have to subtract the value you have from 180 degrees. So if you were at, just round ours to a nice round number, if you were at, 40 degrees north and 80 degrees west, the opposite side of the Earth would be at 40 degrees south, and 80 minus 180 minus 80 would be 100 degrees east. And since, or if you were like actually looking around to our location, the 90 degrees west, you know, oh no, let's not do that. That doesn't make things clear. 80. We're close to 90 degrees west. So that's the one where it ends up being the same. But you switch east and west, and then you subtract what you have from 180. Because, like, for example, 10 degrees east is quite close to 10 degrees west. They're both close to the prime meridian. So if you want to be opposite 10 degrees east, you need to go to 170 degrees west. So this is a diagram sort of showing how you would get the longitude and latitude of Washington, D.C. You rotate around until you reach the appropriate meridian, and then you move up or down until you reach the location. So that's the up and down, 39 degrees north, and then the rotation from the Greenwich meridian is 77 degrees west. Because we live on a ball, our location is expressed with 2 angles. And this isn't exactly the same as our Cartesian coordinate system, because the surface isn't flat, because we live on a ball. So here is a short video about how to read latitude and longitude coordinates and how to find things. And I think, unfortunately, yes.
Anyone who knows me knows I love Royal Kingdom, but not everyone knows why. Allow me to list the ways.
Sorry about the ads.
Latitude and longitude is a coordinate system that is used for locating any place on the globe. The first ever system for locating geographical positions by means of latitudes and longitudes was devised by Greek astronomer named Hipparchus. Today, it is widely used in global positioning systems and in geographical information systems. The Earth is divided up into horizontal lines of latitude and vertical lines of longitude. Latitude is read first, longitude second. Lines of latitude, also known as parallels, are read in terms of north and south of the equator. The starting point is the equator, which is 0 degrees latitude. 90 degrees latitude north of the equator is the North Pole. 90 degrees south of the equator is the South Pole. Note that the poles are at a 90-degree angle from the equator. North of the equator is the Northern Hemisphere. South of the equator is the Southern Hemisphere. North of the equator we have the Tropic of Cancer. South of the equator we have the Tropic of Capricorn. Between these lines are the tropics. At 66 degrees, 33 minutes 44 seconds north and south of the equator are the Arctic and Antarctic circles. Between here and the tropics is the temperate zone. Lines of longitude are also known as meridians. The starting point for reading longitude is the prime meridian, which is a line passing near the Royal Observatory in Greenwich near London in the United Kingdom. This site was chosen as the International Zero Longitude Reference Line by an international conference in 1884. The antipodal meridian of Greenwich is both 180 degrees west and 180 degrees east. West of the prime meridian is the Western Hemisphere. East of the prime meridian is the Eastern Hemisphere. To locate a precise point on the Earth's surface, degrees of latitude and longitude have been divided into minutes and seconds. There are 60 minutes in each degree, and each minute is divided into 60 seconds. For example, the coordinates for the Great Pyramid of Giza is written as 29 degrees, 58 minutes, 45.03 seconds north, 31 degrees, 8 minutes, and 03.69 seconds east. Now to show you how to read the coordinates of a precise point. The first example I will use is Mount Narahoe in the North Island of New Zealand. As mentioned earlier, between each degree of latitude or longitude there is a division of 60 seconds. Right on the line it is 0 to 0 minutes. Then it goes to 01, 02, 03 and so on. At the halfway point it would be 30 minutes followed by 31 minutes and so on until we get to 59 minutes before clicking to the next degree of latitude or longitude where the minutes would return back to 00. Now that I've shown you how to read latitude and longitude, get a map and find the coordinates for these three locations: the Sydney Opera House, Uluru, also known as Ayers Rock in Australia, and Mount Cook, New Zealand's highest peak. Thank you for watching.
So here's some examples getting a rough latitude and longitude. So, for example, here, this hexagon is at, so reading off this map, it's at about 60 degrees north. And going across the top here, it's at 120 degrees west in North America. So if we want to figure out where the star is, this star, well, that's on the equator, sitting on the equator. So that's, if anything, it's a little below. So what, this is 20, 10, 5, it's going to be 1 degree south. And then this is 20 degrees. East. This is 40 degrees east. It's a little bit west of the 40 degrees, so it's maybe 10, 15. Maybe 39 degrees east. And if you were just rounding to the nearest 10 or even 5, you'd probably write this as just 0 degrees south, 40 degrees east, which is what I'm going to do for the rest of these. Then we have the purple circle here. Again, it's a little bit low, but this is sitting on the 100 degree east, and it's just below the 40 degree north. So I'll just write in 40 degrees north, 100 degrees east. The red box is right here. So if we go north and south, this is south of the equator. It's on 20 degrees south. You can see 20 degrees here. So we have 20 degrees south. And then it is sitting on this line here, which is 60 degrees west. And then lastly, we have the blue triangle way down here. Well, this is at 80 degrees south and at 120 degrees west. So that's how you can go through and do this. So basically, you just identify north and south and east and west. This isn't a perfect map because all maps where you're turning a round thing into a flat thing end up distorted in some way. So there are issues with that. Any questions about this? Nope. Okay. So generally maps are designed for some sort of navigation. Since the Earth is nearly a sphere, it's three-dimensional, and most maps are flat, two-dimensional. They're necessarily what are called projections. There are some method by which we take a round, not flat thing and project it onto a flat surface. The places on a map are shown relative to each other, and thus the fundamental frame of reference is the lines of latitude and longitude. Most maps have north at the top. That is just a convention that has been picked up over the years through history. Like if you looked at ancient Egyptian maps, they all had south at the top because that was where the Nile came from. The Nile flows from south to north. And so it totally was natural to put the upper Nile at the top and the lower Nile at the bottom. But it's just an arbitrary choice. It actually has some unfortunate socio-political side effects where we see north is good and south is bad. There are some issues with that, but that is just its convention. There are usually scales on a map. They show you what length corresponds to a certain distance, so you can figure out distances. And the science of map making is called cartography. And putting it together, you do things like surveying and such. So here is sort of an intro to various maps that tell you something about the world or the US or things. And unfortunately, oh no! Ooh.
Number 25. This map divides the world into 7 sections, with each section containing 1 billion people. Number 24. This map shows where 2% of Australia's population lives. Number 23. It may not come as a surprise at this point, but more people live inside the circle than outside of it. Number 22. This map shows what's on the other side of the world from where you're standing. For the most part, it's almost guaranteed to be water. Number 21. Apparently you can't get Big Macs everywhere. This map shows the countries that have McDonald's in red. Number 20. This time the countries in red drive on the right side of the road. Number 19. The countries in white are the ones that England has never invaded. There are only 22 of them. Number 18. These were all of the world's internet connections in 1969. Number 17. These are all the countries that heavily restrict internet access today. Number 16. These countries were all communist at one point. Number 15. These are the countries that don't use the metric system. Number 14. This is a map of where Google Street View is available. Number 13. These are all the landlocked nations of the world. Number 12. And this is what the world would look like if all the countries with coastlines sank. Number 11. This is a map of all the rivers in the United States. Number 10. And these are all the rivers that feed into the Mississippi River. Number 9. This is a rather depressing map of the highest paid public employees in the United States. Number 8. And this is the United States on the moon. Number 7. This is the longest straight line you can sail. It goes all the way from Pakistan to Kamchatka Peninsula in Russia for a total of 20,000 miles. Number 6. This is a map of 19th century shipping lanes that outlines the continents. Number 5. This map shows every country that has ever operated an aircraft carrier. Number 4. This map highlights the countries with the most skyscrapers in red and orange. Number 3. This map shows the world's largest donors of foreign aid. Number 2. These are all of the most photographed places in the world. And number 1. And these are all the places where you can get eaten by a great white shark. If you liked the video you just saw, then feel free to subscribe to our YouTube channel by using the orange button in the top right. And don't forget to go check out our website at list25.com for more awesome lists.
Now a number of those are out of date. Like for example, the one about McDonald's. You'd have to remove some countries. Russia lost McDonald's for reasons. So cartographers use projections to make maps. So a map projection is a way of transferring points and lines on a globe's surface onto a sheet of paper. Now, if you're making a map of a small area, what projection you use doesn't vary much. It's not a huge deal, but it matters when you're doing a map of the whole world. So we're going to go over a few common projections. So the one you've probably seen most often is what's called the Mercator projection. It has parallel lines of latitude and longitude. And it clearly indicates direction in straight lines. So this is a Mercator projection. The lines of latitude and longitude are parallel. All the meridians are vertical. This is sort of a simplified version of the way it's done. You project outwards onto a cylinder from the sphere. It's a little more complicated than this, but it's very useful for navigation because it preserves direction. The problem it has is that it exaggerates size of things near the poles. So Greenland on a Mercator projection looks nearly as big as, looks bigger than South America or similar in scale to Africa. Well, if you actually look at them, Greenland is this big. It's not huge. Africa is enormous. So Africa is enormous. Much bigger than South America is much bigger than Greenland as well. So that's one of the problems, is it exaggerates area, but it does preserve direction. So it's extremely useful for navigating with a ship or a plane or something like that. It makes your life a lot easier for that. Now a Peters projection, which is this one, preserves the size, the area of shapes, but it distorts their shape and direction, so they get sort of stretched and squashed. But the areas are all preserved. So this is a Peters projection. This is a Mercator projection. On a Peters projection, land masses of equal size on the Earth are shown equal size on the map. There's a whole bunch of projections, and if you want to look into them, you can. They can get, more or less ridiculous, but those are the common ones you need to know about. Now, if we're making a map of an area, you could use something like a topographic map. A topographic map is a detailed map that uses contour lines, symbols, and colors to represent changes in elevation and features on Earth's surface. So a topographic map here is such that, so you have some elevated object like this volcano. We use lines that indicate certain elevations to let you know where things are elevated, where things are higher than others, as you can see above. So basically, it's like cutting a bunch of slices through and drawing a line where each of those slices of elevation intersects the ground. And so if you're looking at a topographic map, you can see that there are various features. Now, one of the issues with a topographic map, if they aren't labeled, it's hard to tell the difference between a topographic map where things are going out or up, or when they're going down or in. There are ways to fix that with, adding like a coloring or things that make it clear, but it's an issue. So on a topographic map, there are what are called contour lines. A contour line is a line of equal elevation, constant elevation. And the difference in elevation between two side-by-side contour lines is called the contour interval. So on this one, the contour interval, you can see the step between each line is 500 meters. So the contour interval is 500 meters. On this map, the contour interval is probably 20. So the difference in elevation between two side-by-side contour lines is called the contour interval. And some contours are labeled with an index, with a number. These are called index contours. They're labeled with a number that indicates the elevation. So here we have a 700, two unlabeled contour lines, and then a 640 in the center. And then another symbol that we put on contour maps are what are called hatchers. Hatchers, these little hatches, point down slope. They tell you which way is down. So they point down slope, so they indicate whether this slope is down or up. Which, if you couldn't see the numbers, it would be hard to tell. So this is a short video about how contour maps work and how to read them. They're called contour or topographic maps. And I think on Google Maps there's a topographic map option you want to see it. Pull it up. Well. And here is some sort of terrain map, but it doesn't seem to do anything.
Okay, Shakira, let's play. What game are you?
Sure, let's play.
All right. So, do you prefer old classic?
Sorry about the
Hey there. So the goal of today's video is to better understand what exactly a topographic map is, including what it shows and how to use the different features on the map to help better visualize the area that you're looking at. So let's jump right in. The first question we want to answer is, what exactly is a topographic map? Well, a topographic map, it represents a region, and it shows all of the geographical features of that region, including three-dimensional features like hills and valleys. The ultimate goal of a topographic map is to display these three-dimensional features with ups and downs and cliffs and slopes, rivers and streams, all of these three-dimensional features, but on a flat two-dimensional map. So let's take a look at an example. Here you can see a simple topographic map, often called a contour map. And the feature that should jump out to you on this map are all of these dark, squiggly lines all over the place. Those lines end up being the key to topographic maps. They're called contour lines. So, what exactly is a contour line? Well, those contour lines that you saw running all over the map, those show the shape of the land, and they do it by connecting points that have equal elevation. Let me give you an example. Here's that map again. So if I look at point Y on the map, I know its elevation is 500 meters, and I know that because point Y is located directly on the 500-meter contour line. And so by understanding contour lines, I know that any point on that line is going to have that same elevation. Of course, the other lines represent different elevations, and we'll look at that in a moment. So let's take a closer look. One of the things you might notice is that some of these contour lines, not all of them, but some of them are labeled. For example, the 500 line is labeled, the 600 line is labeled, and these labeled lines have a name. Those are called index contours. And these are contour lines that are clearly labeled with their elevations. Now, unfortunately, on most topographic maps, there's just not enough room to label the elevation of every single line. And this is why we use index contours, maybe every second line or every fifth line or every 10th line, depending on the map. Either way, oftentimes you will be given what's called the contour interval. And the interval tells you explicitly the amount of elevation increasing or decreasing with each line. Now this map is clearly labeled with an interval of 50 meters. And what that means is that as you go from one contour line to the next, there's going to be a change in elevation of 50 meters. So that contour interval tells you the elevation change from one line to the next. Fortunately, even if you're not given the contour interval, you can usually figure out what it is by examining the lines, and we'll see an example of that in a moment. Let's look at some other map features. Most maps are going to include a map scale, and this lets you determine the real-world distances between points as represented on the map. So for example, let's say I want to know how far apart points Y and Z were in the real world. I could use this map scale to figure out how many kilometers apart they are. A future video will take a look at how exactly we use a map scale. Finally, we'll notice that we also have a compass rose, and this is going to tell you the directions on the map and how they correspond with real-world north, south, east, and west. This allows you to orient yourself when using a topographic map. So that's a basic overview of how a topographic map works. Let's take one other look at a different example. So here's another one. You'll notice we have the map scale at the bottom and we have the compass rose down on the right-hand side. We have a bunch of contour lines, and I also see the ocean and some streams and brooks flowing across the surface. We also see a bunch of different points that might represent landmarks or trailheads, anything like that. The one thing I don't notice is there is no labeled contour interval. They're not telling me how much each line is going up or down by. But fortunately, with a little bit of work, I can figure out exactly what the interval is. And that's something that's important to be able to do, especially when we get into more complex tasks like calculating the gradient. So if I zoom into the side of the map here, what I notice is that I do have two labeled index contours. I have the 250 line and the 500 line. And so I want to look at how many lines go in between them. In essence, I want to see how many jumps there are between these two index contours. So I can count them out. Here's 1, 2, 3, 4, and 5. So there are 5 jumps between the two index contours. Now let's do a little bit of simple math. So my change in elevation here is equal to 500 minus 250. Because I know that when I'm walking from one index contour to the next here, I'm going from 500 down to 250 or 250 up to 500. So I know that that difference is 250. So between these two lines, the elevation changes by 250. Now I also know that there have been 5 contour lines here. There are 5 contour lines difference between them. And so if I divide that 250 change in elevation by the 5 contour lines, I get 50 per contour line. And so that means that my contour interval on this map is 50. Now you'll notice I'm not saying 50 feet, 50 meters, and that's because I have no way of knowing. This map is not labeled to tell me what the elevations are measured in. So I'm just going to say 50, or I could say 50 units. So now I know that each line changes in elevation by 50 units. So there's a quick overview of topographic maps. In our next video, we're going to take a look at how we actually draw these contour lines on a blank map. If you like what you're seeing, please remember to subscribe at Mike Sammartano.
So, on a topographic map, changes in distance can be determined using the map scale. The map scale lets you figure out distance. Changes in elevation can be determined by looking at the difference between contour lines. Changes in steepness and gradient can be determined by dividing the elevation change of 2 points on the map by the distance. So if you look at 2 points on the map and you want to figure out the gradient and the change in the gradient, the steepness, the slope between them, you can measure the elevation change divided by the distance they cover. And in general, when you look at a topographic map, areas where the contour lines are tightly packed indicate steep slopes. Areas on the map where the contour lines are further apart indicate a more gradual incline. So on this map, here we have a more gradual incline. Here where we have very tightly packed contour lines, we have steep slopes. So we have a few questions we want to answer about this. So this, unfortunately, doesn't have any units labeled on it. But looking at the numbers and looking at what it is a map of, because this is a map of Hawaii, I'm going to say that these are miles and feet. That should be correct. Let me grab a ruler, because that can help. You really just need something where you can mark down the length you're measuring. You can do it with a bit of string. You can do it with a compass. So if we look at this previous slide, we want to determine certain things. We want to figure out the contour interval, the change in elevation from points A to B, the distance between points F to E, assuming the scale is being measured in miles, distance between C to D, assuming the scale is being measured in miles, the steepness from point A to B, and the steepness from point F to E. So let's write down what we're looking for. I guess I'll erase this. So we want the contour interval. Um, change in height from A to B. Distance. Distance from F to E. Distance from C to D. Gradient A to B and gradient F to E. So let's go through those. Well, the contour interval is easiest to figure out down here. We've got a bunch of contour lines that are all labeled. 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000, 11,000, and then they run out of room to put labels. So our contour interval is 1,000. And it's almost certainly feet. We want to figure out the change in height from A to B. Well, A is at 0, and B is at 1, 2, 3, 4, 5,000. It's labeled, but it's hard to read there. So we have 5,000 feet minus 0 feet is 5,000 feet. Now we want to look at the distance from F to E. For that, well, we need to know the distance from F to E on something like a ruler. You can use a ruler, you can use anything that you can just hold a fixed length with. So here's F to E, and then we can put it up against our scale here. And so that's there. So 5, 7.5, let's say 8, because this is 10. Yeah, 8 miles. Now we want to do the distance from C to D. Put this up to the scale. Ends up about there. So this is 5, 2.5. So that's about 4.5 miles. 4.5 miles. For the gradient to A to B, we need to know this is going to be change in height over change in position. Well, we know the change in height. That's 5,000 feet. We need to know the distance. So we'll measure the distance from A to B. Stick that on our scale. Mark. I would say that's maybe 6.5 miles. So that would be 5,000 divided by 6.5. Which is like 770 feet per mile. Now we know the distance from F to E is about 8 miles. And now we need to think about the elevation from F to E. Well, this is at the peak here. This was 10, 11, 12, 13. So that's from 14,000. So delta H is going to be 14,000 feet minus. This is basically 3,000. Yeah. No, that's for, so what? So this is at 4,000 feet. So this is about 10,000 feet change in height. We have 10,000 feet over 8 miles. And so that is something like 1,250 feet per mile. Let's see if I have, don't have something. So that's sort of how you can go through and do this. So here's another geologic map. This is a geologic map. This is a map that shows what rocks are underground. So the distribution, arrangement, age, and type of rocks located beneath the soil. And it can also show geologic features like fault lines. So each of these colors represents a different kind of rock. And the lines are like fault lines and things like that. So this is a geologic map of the Grand Canyon. And you're seeing different types of rock below the soil. You can also have a bathymetric map. That's a topographic map of underwater features. These are very important. So this is maps of submerged terrain, including underwater mountains, hills, and trenches. These are very important near the coast for navigation, because you don't want to run into an underwater like rock or something and run aground with your ship. That can be disastrous. So that was maps. Let's talk about days. So the day is the amount of time it takes for the sun to go down and the sun to make one apparent revolution around the Earth. What's actually happening is the Earth is making one rotation. Let me see the sun. The apparent solar day is what we see. We see, if you measure the time from when the sun is directly overhead to when the sun is directly overhead, the time it takes between two successive crossings of the same meridian, that is the apparent solar day. So that's from the time the sun is directly overhead to the next time the sun is directly overhead. Now, because we're orbiting around the sun, as we make one full rotation, we travel a little bit around the sun. So it turns out we actually have to turn a little bit more. So one apparent solar day involves the Earth turning about 361 degrees. Just a touch more than 360. A sidereal day is what happens if you measure the time for some star to be directly overhead. So some star will be directly overhead, and then it'll be directly overhead again a day later. That is a sidereal day. So that's the elapsed time between two successive crossings of the same meridian by a star other than the sun. That measures the actual rotation of the Earth. It's 360 degrees. Our time system is based off the apparent solar day, because that's what actually dictates our lives. So the sidereal day is a little bit shorter than the solar day. So 24 hours is a solar day. The sidereal day is 24 hours and 56 minutes. 23 hours and 56 minutes, sorry, misspoke. So here's a short video about the sidereal day versus the solar day. So you can see during one rotation, the Earth travels a little bit about the sun. This is exaggerated, so you can see it more easily. So this is a sidereal day. We've made one complete rotation, but we're not pointed back at the sun again. So to get pointed back at the sun, we have to turn a little bit more, an extra degree about, and that's about 4 minutes. So during the year, we actually make 366 rotations. So here's an even more exaggerated image, so it's even easier to see that if you do one rotation, you travel a little bit around the Earth. So to get pointed back at the sun, it takes a little bit of extra time. The Earth has to rotate through 360 degrees plus 0.985 degrees to complete one rotation with respect to the sun. So a solar day is 4 minutes longer than a sidereal day. So solar day is 24 hours, sidereal day is 23 hours and 56 minutes. This is exaggerated, but it's helpful for understanding this. It also helps for understanding the difference for the moon orbiting the Earth. There's a solar month and a sidereal, there's a synaptic month, which is the month that we see with phases, and then there's the sidereal month. They actually differ by a couple of days for the moon, because the moon travels around the Earth more slowly than the Earth rotates. So a 24-hour day begins at midnight and ends 24 hours later at midnight. That's our standard system of time. So there's noon. Local solar time is when the sun is on the observer's meridian. That is not noon on your watch, especially not here, because we're right near, because we're nowhere near the center of the time zone. So we're off quite a bit from local noon. And then there's also things like daylight savings time. But noon local solar time is when the sun is directly overhead. And the day can be split into two halves: before noon, ante-meridian, AM, and afternoon, post-meridian, PM. 12 o'clock should be treated as 12 noon or 12 midnight. When we say 12 p.m., we usually mean 12 noon. That's the convention, but it should be stated as exactly 12 o'clock is 12 noon or 12 midnight. 12:01 is 12:01 a.m. is at night. 12:01 p.m. is in the afternoon. And in addition, 12 midnight should have two dates associated with it. July 26, 27 would be the 12 midnight, because 12 midnight is in between 2 days. So the Earth is divided into 24 time zones, each containing approximately 15 degrees of the Earth, because 360 degrees splits into 24 segments of 15 degrees. And that's because the Earth rotates about 15 degrees an hour. So each contains approximately 15 degrees of longitude, or 1 hour. The first time zone begins at the prime meridian and extends 7.5 degrees both east and west. And the centers of each time zone are multiples of 15 degrees. Those are the base time zones that this is all built off of. determining the time zones was actually what the conference that determined what the prime meridian was. And then those time zones are bent, distorted, mangled, etc. by politics for what actually gets used. So here's the US. These are the centers of each time zone. You can see the time zones for each of these. Central is wider than it should be, sort of this way. We're on the edge of a time zone over here. We're in this little funky little divot here. But these are the US time zones. For standard time. So, you know, there's Eastern, Central, Mountain, and Pacific. And then there's Alaska Standard Time and Hawaiian Aleutian Standard Time. And as you travel west, you gain time. Actually, it is the end of class. So we'll stop there for now. I'll continue this next time. I'm still grading the tests. I'll have the grades up soon, probably by Monday next week, certainly. Yeah. Let's see how far off I was from where I wanted to be. I'm gonna stop sharing and